Let's continue ZEUS training. Section 2, ZEUS input data structure. So the ZEUS input data structure is identical to that of ZEUS. We can have comments scattered throughout the entire input deck, and then we have the input deck split into three sections. We have the executive control section, the case control section, and the bulk data section. In the executive control section, you'll import the FEM solution. You can also optionally import matrices. You can have diagnostic codes, and then cend is the command that signifies the end of the executive control section. Then you move on to the case control section, which controls the modules that ZEUS will run. So you can have a title for the overall input deck, and then you have an echo option. I usually have echo equals sort, which will echo the input deck to the output deck so you can be sure of what your input was for a particular output file. And then you can have one or more subcases delineated by the subcase equals, and then you can have a subtitle and a label associated with each subcase. The case control section then ends with the begin bulk command, which leads to the bulk data section, which makes up the majority of the input deck. Shown here is an example where we have the arrow Z bulk data card. And then the bulk data section ends with the command end data. And then, as I said, the comments, which start with a $, can be anywhere within the input deck. The $sign must be in the first column or the first character of a line. There are some bulk data cards which can have a $sign embedded in one of the fields. In that case, that $sign does not signify a comment. It signifies an integer that refers out to another bulk data card. So the comment $sign must be on the first character of a line. Additionally, the input deck or the ZEUS input reader will only read the first 80 characters of any given line, no matter if you're using the free format or the fixed format. So any characters after the 80th column is ignored. So in this case, in the bulk data section, you can see that we've got a little helper comment string which lines up the fields for the fixed format. So the first field here is 8 characters long, and then the second field once again is 8 characters long. So this integer 0 is the second field of the arrow Z bulk data card. And then we have the character string yes, where the field name is xzsim, and this is the third field of the arrow Z bulk data card, and so on. The 10th column is reserved for continuation lines. So in this particular instance, the arrow Z card itself is made up of 2 lines. So in our continuation here, we have plus arrow, and then the first field of the second line here, we have plus arrow, which matches. So that signifies that this line is a continuation of the arrow Z bulk data card. So let's talk about the executive control section. We have the assign FEM command, which imports the structural modal data, and this is required. We have the assign matrix, which imports matrix data by the output 4 format, and this is optional. The cend signifies the end of the executive control section. CPU allows you to specify the number of cores to use for parallel computation using OpenMP. In this case, all of the cores must be on the same machine that's running the ZEUS job. Next, we have mpiCPU, which specifies the total number of CPU cores used by the MPI, the message passing interface parallel algorithm. In this case, it does require additional setup, but these cores can be spread out among multiple physical machines over the cluster. You can have both CPU and mpiCPU. In this case, the total number of CPUs that is used by ZEUS would be CPU times mpiCPU. So for example, you can set CPU equals to 4 and mpiCPU equals to 2, where the first mpiCPU would be on the local machine and the second MPI would be on a different physical machine. In that case, 4 CPUs on the local machine would be used, and 4 CPU cores on a different machine would be used in the ZEUS computation, for a total of 8. Next, we have the descend command. This activates the linking of dependent geometry parameters. Diag for diagnostic output. You'll almost never use this option. Memory is the maximum memory in terms of megabytes that can be allocated by ZEUS from the heap space. The default is quite large. However, you may need to use the memory command to specify more memory in some instances. The solution command, which can be abbreviated as SOL, alters the solution sequence. And then finally, the $, as we've seen, is the comment statement. So this is an example. We have the assign FEM command. The assign FEM and assign matrix can end in a comma. These are the only 2 cards that support that feature. This allows you to break up the assign FEM or the assign matrix onto 2 lines. This is useful in particular if your file name is quite long, which could be the case if your solution file is in a different directory. So if you have to go up 2 or 3 levels, you'd have ... ///, and then if you go down more directories to a file, you could imagine that this string can get quite large. So in my inputs, sometimes the assign FEM equals, and then file name takes up one whole line, and I'll have comma. You can switch to the new line, and then you can have the format, boundary condition, print, and support options on the second line. Then the assign matrix imports a matrix. Once again, assign matrix can support the comma, new line option. And then we have some more of the cards as an example here. And as I said earlier, the entire length of any given line can only be 80 characters long. ZEUS will ignore anything beyond 80 columns. So this is the assign FEM. This is required. At least 1 assign FEM must exist, and no more than 2 can be specified. You can have 2 in this example here, where your structure model is a half model, and so you have the symmetric and the anti-symmetric solutions. So you can import both the symmetric and anti-symmetric. Usually nowadays, your models will be full span, in which case you can only import one solution. So we have assign FEM equals file name, and then form, boundary, print, support, and Aset. For Nashran, the following commands must be set. Echo must be equal to sort or both. This is so that ZEUS can read in the required information. So in this box here, we have the required information that ZEUS needs. It needs to be able to read the grids, the coordinate transformations for those grids. So this would be the echo input, and then it needs from the output, the Nashran output, the natural frequencies, the generalized mass and stiffness, and the mode shapes, or the eigenvector. Now importantly, ZEUS does not need to know the connectivity and the property cards of the finite element model. Therefore, if you want to protect that information from one group to another, or if you're sending this output file to some other company to do error elastic analysis, you can either manually delete the Nashran bulk data cards that are not associated with the grid and coordinate transformations, or in your echo equals sort, you can use this command to only select the coordinate cards. So we have the chord 1C, chord 1R, chord 2C, chord 2R, and chord 2S, and then the grid and S point. So this will pick up all of the grids, the S points, and the coordinate cards. In this case, Nashran will not output your mass like ConM2. It won't output your elements like the C quads, and it won't output the property cards. So you can protect that information, but you'll still have the eigenvector, which is all ZEUS reads. Now for Aset equals yes, additionally you must have S vector equals all, so that ZEUS can read the eigenvector associated with the Aset. And then if Aset equals no, you either need displacement equals all or displacement equals n. We recommend displacement equals all, so that ZEUS will, or Nashran will print out all of the grid displacements, so ZEUS can read in the full eigenvector. Now, if you omit structure grids by using the displacement equals n, so you have a set, or S vector equals all, this may also exclude some structural masses if the masses are attached to the omitted structural grids. This may give discrepancy in the distributed inertial loads computation that is normally a part of the trim analysis and dynamic loads analysis. Therefore, it's the user's responsibility to ensure all the structural masses are included in a ZEUS analysis. And so for this reason, the vast majority of cases, I use displacement equals all so that all of the structure grids are included. This is an example Nashran file. So we've used the echo, echo equals sorted here, and then the displacement equals all. So then in the sorted bulk data echo, you can see that we've got the Aset card and we've got our grids. And so ZEUS will read this information from the Nashran output. Next, ZEUS will look at the real eigenvalues. So it looks for this string real eigenvalues and then parses out this data. So in this case, we have 5 modes. So it will read this information here, the eigenvalue, generalized mass, generalized stiffness. And then next we go on to the eigenvectors. So ZEUS will build up the phi matrix, or the eigenvector, by parsing this output here. So we have the grid points here, which of course would match the grids up in the input. And then we have the grid displacement in each of the 6 degrees of freedom for each grid. Moving on, the form in the assign FEM specifies the FEM solver that generates the structural output file. Use form equals MSC for MSC Nashran, which is what we've been seeing so far. Additionally, ZEUS supports NE Nashran, Astros. Astros is finite element code by Zona. And then we have Ideas, Abacus, Altair, and Free for the free format, and Acquire to acquire a previous FEM solution. So if you have a code that's not listed here, you can write your own converter to convert that to the free format. The free format is described in the ZEUS user's manual. And then the acquire option, that's talked about here on the second bullet point here. For a large finite element model, importing the structural solution could be time consuming. Therefore, the user can use the FEMSave bulk data card to save the FE solution onto a data file, and then use form equals acquire to retrieve it. So in this case, ZEUS won't have to parse the finite element method output file. It can just directly load the data from the save file. Next, we have the boundary condition. So boundary can be sim for the symmetric boundary condition, anti for the anti-symmetric, and asim for the asymmetric. So asim would be for the full span model, and sim and anti would be used for half span models. And of course, the specified boundary condition will affect the downstream disciplines such as flutter and trim. Next, we have the Aset option. If Aset equals yes, that allows ZEUS to use the Aset degrees of freedom of the FEM for the static and dynamic air elastic loads analysis. And if Aset equals yes, then only those structural grid points specified in the Aset and Aset1 Nashran input are used by ZEUS. S vector equals all must be specified in the Nashran case control section. And additionally, to compute the inertial loads for the static or dynamic air elastic analysis, it's required to import the SMAA or the AMAA matrix from ZEUS. If Aset equals a no, then for these analyses, you would import the MGG matrix. This Aset option is only available for the MSC Nashran format. Next, we have the support. Support is an optional input to specify the degrees of freedom of the rigid body modes of the FEM. Now, if you're only doing a flutter analysis, support strictly, it's not really required. But for the other options, it is required to tell ZEUS which modes are the rigid body modes. So our recommendation is, if you have rigid body modes in the output, to always use the support option. So for example, for a full span model, you would have support equals 1, 2, 3, 4, 5, 6, where those specify the degrees of freedom of the rigid body modes. For a symmetric case with 3 rigid body modes, then support would be 1, 3, 5. Is that right? Yes, 1, 3, 5. And then for the anti-symmetric, support would be 2, 4, 6. Now, if the integer representing the component numbers of the rigid body degrees of freedom is negative, then ZEUS will perform the following tasks. 1, it replaces the imported rigid body modes by the program computed rigid body modes, and then it forces the natural frequency and the generalized stiffness of the rigid body modes to be 0. So this is usually a good thing. So once again, if you're using the support, we would always recommend to use the negative option. So for a full span model, you would have support equals minus 1, 2, 3, 4, 5, 6. The support degrees of freedom is defined in the Nashran local coordinates, and the support specified will affect the downstream disciplines such as trim, maneuver loads, ejection loads, gust loads, and nonlinear flutter. Now for trim, support is required to compute the distributed inertial loads of the free structure. And then for the maneuver loads, ejection loads, gust loads, and nonlinear flutter, support allows the user to correlate the rigid body unsteady aerodynamics at 0 reduced frequency with the static aerodynamic stability derivatives. And the MLD stat card is additionally available, which can be used to transform the rigid body modes to airframe states. So this option requires the use of support so that ZEUS knows which modes are the rigid body modes. Next, we have the assign matrix command, which allows you to import a matrix that is in the output 4 format. So the form of that here is assign matrix equals file name, and then form equals the form, m name, which is the matrix name, and then the print option. So here's an example where we're importing the MGG matrix. So the matrix name is demo1.mgg. It's ASCII formatted, and the matrix name is the MGG. Here's a second example where we're moving to a different directory. So we move to the parent directory and move to the export subdirectory, the home subdirectory, the ZEUS subdirectory, and then finally demo2.mgg. Also note the / works for both Linux and Windows. So I always use a / so that the input deck is compatible with both Linux and Windows. If you use a / it will only work on Windows, and if someone copies your input and tries to run it on Linux, they'll get an error. Also remember, for Linux, the paths are case sensitive, so you have to make sure that the case is correct in the case of Linux. So the form indicates the format of the data on the external file. So format is for the ASCII format, unformat is for the binary format, and then R format is the ASCII non-sparse format, and the R unform is for the binary non-sparse format. So in the case of huge matrices that are stored in the non-sparse format, using R format and R unform will be faster than using format or unformat. For smaller matrices, it doesn't matter, and you can just use format or unformat. Mname is the name of the matrix. If the mname is not specified, then the name of the matrix is specified in the header record of the output for format. Then that is used as the name of the matrix. Sometimes that name will be correct, sometimes it will not be correct, so I always use mname to override what is in the file itself. And here's an example of a ASCII output 4 format file. This is the MGH, so this is a case where you would need to use mname, because from Nashran, the name of this matrix is just MGH, but in ZEUS, the name of the matrix is either SMGH or AMGH. S for the symmetric or asymmetric, and then AMGH for the antisymmetric. So the mname option would have to be used with this file. Next, we have the Nashran DMAP alter cards that you can use in Nashran to generate these files. So here we're exporting the mass or stiffness matrices to a file. For the ASCII and non-sparse matrix, and now here we're showing the MGG. I would recommend the MGG to use the sparse. Oh yeah, right. Actually, it doesn't matter because the output 4 format is kind of a sparse format. So for the MGG, you can use either the non-sparse or the sparse, and it'll work just fine. But anyway, you have assign output 4 equals the matrix name. Then we have the status equals unknown, unit 12, form equals formatted. So this will specify the ASCII file. We're running solution 103, and then our alter statements are here. So we have the compile, SE mode, su in equals MSE, su no list, and then we have alter strain energy, and then this output 4 command will output the matrix. So output 4 MGG. This 16 here specifies full double precision in the ASCII format, and then we have end alter and cend. Now for the sparse matrix, we change the unit number to negative. So here our unit number is positive 12. For this sparse option, we use minus 12. Everything else is the same. Now if we go to binary and non-sparse, the form, instead of formatted, we change form to unformatted. So that signifies binary. And now for binary, sparse, and big mat, form is still unformatted. Our unit number is minus 12, and then we have true specified in the big mat option to force this matrix to use the big mat option. Now with Nashran, this really isn't needed because Nashran will automatically use the big mat format if the matrix is too big to store otherwise. So why do you want to import the GSET mass matrix? Let's talk about that. To compute the inertial loads at the GSET degrees of freedom requires the GSET mass matrix to be imported by the assign matrix command shown here. The MGG name is a hot-wired matrix name assigned by the program to store the GSET mass matrix. And as we just saw on the previous slide for MSE Nashran, MGG is obtained by the DMAP alter statements. Now the MGG is required for these two scenarios. The first one for dynamic loads or the trim analysis, if the output of the GSET loads is requested by the user. Our inertial loads are MGG times X double dot, which is MGG times phi S times C double dot plus phi C times delta dot. This is the phi S is associated with the symmetric or asymmetric boundary conditions, and then phi A in this equation is associated with the antisymmetric boundary conditions. And then phi C is the control surface modes that are computed by ZEUS. MGG times phi S is called SMGH, and MGG times phi A is called AMGH. So from Nashran, you can either output the MGG matrix alone, and then ZEUS will compute SMGH by MGG times phi S, or from Nashran, you can do this multiplication and output the MGH matrix from Nashran and then import SMGH directly, and ZEUS will use that. However, you still need the MGG to compute this MGG times phi C. Now, MGG times phi C is used to create MHC. So MHC is involved in the closed loop state space equation. The MHC is the inertia coupling matrix due to control surface, and it's defined as either phi S transpose times MGG times phi C for the symmetric asymmetric case, or phi A transpose times MGG times phi C for the antisymmetric. So once again, you can see that MGH, SMGH, or AMGH can be used to compute the MHC. Moving on with executive control commands, solution. This allows you to specify a negative integer to stop the program after the execution of certain modules or to go directly to another module. Usually this won't be used, but solution -1 stops the program execution after the computational mesh is generated. So if you're working on creating the aerodynamic mesh, you can specify solution -1 so that ZEUS will stop as soon as the mesh is generated, and it won't go on and try to execute the following modules. So that's useful as you're setting up the aerodynamic model. And then solution -2 stops the program execution after the spline module is completed. And if you have plot mode bulk data cards, then the files for the interpolated mode shapes will be created. So once you finish the aerodynamic model and you're moving on to set up the spline, once again you can specify solution -2, and ZEUS will terminate as soon as the spline finishes. That way you can verify that your spline input is correct. And then CPU is for the OpenMP parallel computation. So this works by using CPU n, where n is an integer, and n is the number of CPUs for the parallel computation in the Euler solver. This figure shows a typical savings of computational time versus the number of processors. Going from 1 to 2, you can get close to 50%, but then beyond 4, your savings start dropping off. So if you have a lot of jobs to run, the most efficient way is just to use one CPU for each individual job and run as many jobs as you have. However, of course, each job requires its own memory, whereas using multiple CPUs for one job does not increase the memory requirements. It might increase just by an insignificant amount, but not by much. But with 4 CPUs, you can see we're about 30% computing time versus, of course, 25% would be ideal. And out at 8 CPUs, we're still sitting above 20%. And then next we have mpiCPU, which is the number of processors for MPI. So this defines number of processors to perform the parallel computation using MPI. And much like the CPU command, you'll specify mpiCPU n, where n is an integer. Now for the time domain, aeroelastic simulation modules, M-loads, Nancy, nonlinear flutter, and E-loads, the computational mesh can be divided into several subdomains using the block MPI bulk data card. In this case, the Euler equation can be solved concurrently on each subdomain using MPI parallel computation, and within each subdomain, the OpenMP, which is the CPU command on the previous slide, can be applied using the CPU executive control command to have parallel computation in the time-accurate Euler computation. Now for generating the frequency domain, generalized aerodynamic forces, using the linearized Euler solver, the gaffs of all reduced frequencies K and mode shape pairs, which we call K-mode pairs, can be computed in parallel using MPI computation. So this is an embarrassingly parallel computation. So if you have NK, NK is the number of reduced frequencies, and M is the number of modes. That is how many K-mode pairs you have. So say you have 20 modes, and then you have 8 reduced frequencies. That would be 160 K-mode pairs. So N can be up to 160. And ZEUS, if you have 160 cores available in your cluster, setting mpiCPU 160 will send off each K-mode pair task to each MPI core. And so you'll compute them all at the same time because each K-mode pair can be computed independently of one another. So for most efficient computation, if you set n equal to nk times nm, that would be most efficient. And then for additionally, in the GenGAF module, if you have control surface kinematic modes, then we have additionally nk times nc should be added to that list. So if you have 4 control surfaces and 8 reduced frequencies, that's 32 additional K-mode pairs that must be computed. And then for gust, that is just one additional mode, so it's just nk times 1. So of course you can combine all of 3 of these together. So if you have 20 modes, 4 control surfaces, and 1 gust, that would be 25 times nk. And of course n could also be some factor of that quantity. So next we have the case control section. So we have the begin bulk, which ends the case control section and then begins the bulk data section. Echo controls the echo of the bulk data section. And then we have our modules. So we have ejection loads, flutter, GenGaf, G loads, maneuver loads, nonlinear flutter, stability derivatives, and trim. And then we have more non-subcase cards. So label provides an additional description of the subcase by a character string. Subcase delimits and identifies a subcase section. Subtitle defines the subtitle for each subcase, and then title gives an overall job description. So the case control section may contain many subcases. Title and echo must appear before the subcase section, and subtitle and label must appear within each subcase section. So the title, subtitle, and label, the string descriptions can be up to 72 characters. And then we've talked about those other cards. These are the discipline-related cards, and at least one and only one discipline must be selected within each subcase. So if you want to run Flutter and G loads, that would be 2 subcases, so you need 2 subcase cards, and then each of Flutter and G loads would appear within each subcase section. So here's an example, case control section. We have title, echo equals sort, and then we have the first subcase. So within this subcase, we have a subtitle and a label, and then this is a Flutter analysis. So the Flutter equals 10 will refer to the Flutter bulk data card with ID 10. We then have a second subcase. So after the first subcase finishes, ZEUS will then move on to the second subcase. For the second subcase, we have a subtitle and label, and then this is a trim analysis. So the trim equals 110 will refer to the trim bulk data card with ID 110. And then the case control section ends with the begin bulk command. Next, we have the bulk data input section. So this begins after the begin bulk case control command and ends with the bulk data card end data. The bulk data section contains bulk data cards that specify the geometry of the aerodynamic model, the spline for the displacement and force transferal between the structural finite element grid points and the aerodynamic boxes. It defines the Mach number, reduced frequencies, and aerodynamic methods for the unsteady aerodynamic data generation, and the disciplines to be analyzed, which could be flutter, trim, maneuver loads, ejection loads, gust loads, nonlinear flutter, and there are a few others as well. And then we have other miscellaneous input. So as I said earlier, we have 2 options for the input, either a fixed format or a free format. I use the fixed format exclusively because it makes the input file, everything's lined up nice and neat, and it's easy to read. So each individual field is 8 characters. We have up to 10 fields, which gives us a total length of 80 characters. ZEUS will ignore anything after the 80th character. So here's an example of the AE fact card. So AE fact will take up 8 characters. So in your input deck, you would have AEFACT space, and then you have the integer 100. This 100 can appear anywhere within the 8 characters of the second field. And then we have 0.0 in the third column. So what this means with these numbers appearing anywhere within the column, for example, column 2 could have five space characters and then 100, and then immediately you could have 0.0 and then 5 more spaces. So when you look at the text file, the 100 and the 0.0 would be right next to each other. So it would look like 1000.0. but since the 100 is within the 8 characters of the second field and the 0.0 is within the 8 characters of the third field, ZEUS will grab the 100 and say, okay, that's in the second field. It'll grab the 0.0 and that's in the third field, and it will interpret it correctly. The 10th field has the continuation line markers. Now, unlike Nashran, unique continuations are not required, and continuations cannot be separated except by comments. So in this example, our continuation character is plus A, and then so in the first field of the following line, we have plus A as the continuation string. And then once again, we reuse plus A, and then we have plus A again. This makes it a lot easier to input your continuation lines. You don't have to make sure that they're all unique. You could also just use the plus character if you would like. Also, the continuation can be blank. So your AE fact card here in the 10th field can be completely blank, and then the continuation line would have 8 space characters in the first field, and then you would have the numbers. I don't like using blank because it's a little bit harder to read. Because when you look at the first line, it's ambiguous. Oh, well, if this is blank, do I have a continuation line or not? You have to look and see, is there another line after this? So I always use characters. Usually I just use the plus character alone, and that signifies the continuation line. But of course, if you'd like, every single continuation string could be a unique string. Next, we have the free format, where you can ignore this whole lined up 8-column thing and just use commas to separate the fields. So in this case, we have AE fact comma and then 100 comma. If we have a blank, which is not allowed for the AE fact card, but let's say we had a bulk data card where blank is allowed, you just add an extra comma, and that signifies that we have a blank field. The spaces before and after the commas are optional. So if you want, you could just do away with all of the spaces. But in the free format, you still have the 80-column restriction. So just be aware of that. You still cannot go beyond 80 columns. Basically, the only time I use the free format is if I have a param bulk data card. So you can type param, comma, and then the name of the parameter, comma, and then the value. So you don't have to worry about lining it up with the 8 columns. But other than that, I always use the fixed format. I find the fixed format much easier to read.